Department of Collegiate Education, Digital Learning. So this is a video on BSc Physics Semester 3 Unit 1 Electricity and Magnetism. Electricity and Magnetism Unit 1 Network Theorems contains Maximum Power Transfer Theorem statement, proof for maximum power delivered to the load, power transfer efficiency. So in this we'll be learning about maximum power transfer theorem. So we'll see what the statement is. A load will abstract maximum power from a network when its resistance equals the resistance of the network as viewed from the output terminals with all voltage sources removed, leaving behind the internal resistances. That means if there is a complex network, as we have learnt already, any complex network can be simplified using a Thevenin's theorem. So the equivalent circuit will have a single source of voltage VTH, and instead of many resistance we have a single resistance RTH. So that is connected to the load. So the complex network can be simplified by Thevenin's network. What the maximum power transfer theorem states is, when the load resistance, you can vary the load resistance. If you adjust the load resistance such that the load resistance is equal to the internal resistance or the Thevenin's resistance here, then maximum power will be delivered to the load. So this kind of maximum power transfer is useful for analyzing electronic and communication networks where it is important to transfer maximum power to the load irrespective of the efficiency. So proof of maximum power transfer theorem. So as we have discussed earlier, a complex two-terminal network, linear bilateral two-terminal network, can be simplified by a Thevenin's theorem, and this is the Thevenized equivalent circuit. So the original two-terminal circuit is replaced with a Thevenin's equivalent circuit across the variable load resistance. So the load resistance can be varied here. The current through the load for any value of load resistance is, so in this circuit, Thevenized equivalent circuit, the current, load current IL, is given by voltage, that is the EMF of the battery, divided by total resistance. As these two are in series, total resistance is RTH plus RL. So the load current is equal to VTH divided by RTH plus RL. EMF divided by the total resistance. Total resistance is RTH and RL. So the power absorbed by the load is PL is equal to I square RL. Power expression power is current square, current through the load into load resistance. So current through the load is, from the first equation, VTH divided by RTH plus RL whole square into RL. So power is VTH divided by RTH plus RL whole square into RL. This P is equal to I square RL is called as Joule's law. Joule's law of power. So this power will be maximum when this equation, this is a mathematical equation. The mathematical equation here in this equation, RL is a variable, VTH is constant, RTH is constant. As you vary the load resistance, power will vary. Power will be maximum when the first order differential equation dPL by dRL is 0. So we know from mathematics, whenever a quantity is maximum, its first order derivative will be 0. dPL by dRL is 0. So if you differentiate this equation for power, differential of this equation with respect to RL. RL is a variable here. VTH is constant, RTH is constant, RL is variable. So if you differentiate this by applying product rule, so in the first term we have RL, in the second term also we have RL. So if you differentiate the equation using the product rule and equate the differential to 0, then we get a condition that RTH is equal to RL. So if you differentiate this, so keeping the first term constant, differentiate the second term. So we keeping VTH divided by RTH plus RL whole square into RL by RL is 1. Next, keep RL constant and differentiate the second term, you get this. Then if you simplify this, you will get this term. So this is equal to 0 because condition for maxima is first order differential with respect to RL is 0. So VTH cannot be 0. So whatever is there inside the bracket has to be 0. So if that is 0, 1 divided by RTH plus RL whole square is equal to 2RL divided by RTH plus RL whole cube, which is nothing but RTH is equal to RL. That means we are varying the load resistance here and finding out the power. Power will be maximum when the condition for maximum is PL will be maximum when RTH is equal to RL, Thevenin's resistance of the equivalent circuit is equal to load resistance. We get maximum power. That's what. When RL is 0 in this equation, if we put RL is equal to 0, then power will be 0. As you increase load resistance, power increases, becomes maximum, and if you further increase, it will decrease. So maximum power does not guarantee maximum efficiency. So the maximum power transfer occurs when the load resistance is equal to the Thevenin resistance of the circuit. That's what we have proved just now. The maximum power transfer occurs when the load resistance is equal to the Thevenin's resistance of the circuit. So by substituting RTH is equal to RL, we get the maximum power delivered to the load. So the efficiency of the equivalent circuit is equal to output power divided by total power delivered by the circuit. Efficiency is given by the output power delivered to the load divided by total power delivered by the source. So output power is nothing but I square RL, load power dissipated at the load. Power dissipated at the load is power is given by current square into resistance. So I square RL divided by total power. Total power is there is a power dissipation across RTH and power dissipation across RL. So it is nothing but I square RTH plus I square RL is the total power. But we know that RL is equal to RTH. So if we substitute RL is equal to RTH in maximum power transfer, RL will be equal to RTH. So I square RTH divided by I square RTH plus wherever we have RL, replace it by RTH. So this will be equal to half. So efficiency is half. In terms of percentage, efficiency is 50%. So this theorem, even though it says that maximum power is transferred when RL is equal to RTH, but it does not guarantee maximum efficiency. Efficiency is only 50%. But for low power instrument where the power itself is low, efficiency does not matter much. So even if the efficiency is low in communication electronics, this condition may be used. RTH or maximum power condition is used in low power instruments. So these are some of the references. Students can refer these for better understanding of the topic. Thank you.